let's conduct an ANOVA using SPSS. I'm going to start by grabbing some data, and this is in the means testing ANOVA section, the MSLQ. We've used this quite a bit already. So we've got lots of variables as usual. I know which ones I'm going to focus on. So what I'm going to do is I'm going to copy. I'm not going to sort the data in advance. I'm just going to pull it all over and do the work in SPSS. Now, you might not want to do this. You might want to organize yourself in a different way. I'll paste the data in. So the two I'm going to focus in on are 2 and 16. I did actually miss a column when I did this. But 2 is grade, and 16 is post-self-efficacy. I'm just going to label those so we have them to go with. And we're going to go back to data, and we're going to do the analysis. Now, normally you would conduct your frequencies to get your descriptives first. I'm going to skip that today because I think we're familiar enough with that process, and you can do that. So we're going to go to Analyze, the General Linear Model, and Univariate. Click on that. So grade is going to be our fixed factor, our independent variable, 3 levels of independent variable, grade 9, grade 10, and grade 11. And our post-test self-efficacy will be dependent. So does grade impact self-efficacy? We're going to also put some options on this. So we're going to come down to this options button. And we're going to click on the descriptives, the homogeneity test, and the effects, estimates of effect size. We want the descriptives you can or cannot do, but I'm going to do it because I need something to talk about with you. So I'm going to continue. I'm going to run that. Let's just look at the descriptives, get a sense of what's going on. Our standard deviations are all fairly the same, a little bit around 1, 1.15, 1.3. They look pretty consistent. We have 37 ninth graders, 75 10th graders, and 16 11th graders. Not great distribution, but you know, when you're doing an experiment, sometimes you get what you get. And here are the means: 4.7, 5.0, and 5.7. So we're going to see if there's going to be a difference in these means. Are these means statistically significantly different from one another? The ANOVA is an omnibus test, meaning it just kind of shows you where it is. It's the overarching thing. If you want to figure out what's in the omnibus, you have to dig deeper. So the first thing we want to do is check equality of error variances, homogeneity of variances, that's sometimes called. And we're going to do that on pulse self-efficacy, the Levine's test. And remembering, we want curves to look similar. So we want statistical similarity. We want good overlap. We want the shapes of the curve to be basically the same. And so above 0.05, we're in good shape. So if we look on post-efficacy based on the mean, because this is a means test, we see it's 0.11. That is above 0.05, meaning there is no statistically significant difference between the equality of error variances. Or the curves basically have the same shape or close enough that we can do the next step. Then we go to our ANOVA test, and we can see the results of the ANOVA test. And as we discussed in the previous video, we're going to look for the models. Now all the numbers come out in the models here, so when we write this up, we use this information to write things up. So the line we're most concerned about is our variable 2, which is our grade level. We see our sum of squares, degrees of freedom, mean square, the F value, and the significance. So, and then we have the other reported values as well, the error and the total. And let's take a look at what we got. So again, F is the test statistic. So that's the value that you report as the test statistic. What we care about for interpretation purposes is the F statistic showing statistical similarity or statistical difference. And here we can see it's 0.019 or 0.02. That is below 0.05. So there are statistically different results. So the results are statistically different. So again, if we go back to the means, we know there is something different going on here. And maybe the 4.7 is different than the 5.0, and maybe the 5.0 is different from the 5.07. We can't tell just by looking at the ANOVA results. The ANOVA gives us the omnibus. There is something different. And then we would have to do a follow-up or post hoc analysis to determine where the difference is located. And now to interpret our effect size, we have a 0.061. So if you need, and this is for partial eta squared. Remember, partial eta squared is different from Cohen's d, which we used on the t-test. So what I'm going to do is I'm going to actually run over to my wiki, my Practical Stats for Educator wiki, to just check the results. I would comment, there are a couple of places effect sizes are reported. There is an effect size reporting here. This one is for Cohen's d, but we want to find the one that says rules of thumb for interpreting effect sizes of ANOVA. We'll click on that. And we can see we have a medium effect size. So there's some impact. So de facto, being in a grade is increasing your self-efficacy in STEM in a decent way. Next step is to write this up. We have an ANOVA template that we can use for the purpose of writing this up. We're going to state the research question. The impact of grade on, I'm going to specify 9, 11 on self-efficacy as measured by the MSLQ. Our independent variable is grade, and there are 3 levels to the grade, 9, 10, and 11. Check the data, you'll see it, and the dependent variable is self-efficacy. State the null. There will be no statistically significant difference in grade. I think I spelled that wrong. Significance in grade 10, 11 on self-efficacy. The alternative, there will be statistically significant difference in grade 10, 11 on self-efficacy as measured by the MSLQ. I'm going to put that up here too. Just a little more detail saying how we're measuring self-efficacy. I think it's worthwhile. Set the criterion for rejecting the null. As always, we do 0.05. Okay, then we're going to compute the test statistics. The Levine's test is the homogeneity of variance. We do that first. And so we can go back to our Levine's test. The Levine's, so the F is degrees of freedom 2, 125. So the Levine's F. So we're going to say F, and we do report our degrees of freedom, 2, 125 equals 2.24. And the P is 0.11. So we see that we have homogeneity of variance. There's no statistically significant difference, homogeneity. Now we go back to the data and get our F data, which would be on this line right here. We're going to pull the variable and the error. So we'll put our F, our degrees of freedom, 2, 125 equals 4.07, and our p-value for this is 0.02. Now our next step would be to conduct the post hoc analysis. We'll do that in a separate video so we can interpret the results. Stay tuned for the next video where we take our omnibus results and dig down in post hoc analysis to figure out what it all means.